Hello, everybody. So that's me, Mira and Ragnar, will present you REACTIVES, a language for interactive distributed applications, but we will start right away with a demo of a toy REACTIVES application, and Ragnar will do this, and I will take over after this. So Ragnar, floor is yours.
Thank you. So we'll start with this concrete example, the TODO MVC case study, an application I believe you're all very familiar with. It reacts to user input by updating its internal state and displaying that back to the user. You can also modify the state, resulting in this time-changing behavior typical for this kind of application. And while this is a small example, I believe you can all see how realistic applications are composed out of these basic principles. Now, I don't want to talk too much about a single instance of this application, but rather about multiple instances, because even I own multiple devices, or I may want to collaborate with my colleagues. And to do so, we first connect device A with device B using this three-way handshake here to establish a WebRTC connection. Once the connection is established, the two devices are synchronized. You now have to see, so we can build multiple of these pairwise connections. Let me just move this one here, to form arbitrary peer-to-peer topologies of these connected devices, synchronizing their changes. Now, in every peer-to-peer system, you have to consider what happens in the case of failure. Say, when device B crashes and is restarted, which I'll simulate here by reloading the frame containing device B. Now, first, you don't see much. The state is transparently restored. However, changes on the devices are no longer synchronized, but you can still work offline. Once the devices are reconnected, they start propagating changes to each other again. And most importantly, once all of the devices are connected to each other, the state of all devices is consistent, a property known as eventual consistency. Now, the point here is not that eventual consistency and offline availability are unsolved problems, but rather that they are a baseline that all applications of this type require. So developers should not have to implement these on their own all of the time, but rather these should be basic tools in the toolbox of every programmer, like lists are, like maps are, that they can just use and that work. And how such a toolbox looks like and how it can be implemented is what we'll show you in the rest of the talk at the example of REACTIVES. And with that, Mira, the floor is yours again.
Okay, thank you. So Ragnar just said that our, let's say, answer to the requirement that developers shouldn't be forced to re-implement support for offline availability and eventual consistency over and over again every time they implement an interactive distributed application is REACTIVES. So he said a set of toolbox. At the beginning, I said a language, what the hell it is. We call it a language, a reactive language, and the name says it's embedded into Scala, but actually is basically a set of APIs and a set of libraries in Scala. So technically, it is a set of toolbox, a set of building blocks. Okay, let me jump right away to show you a snippet code for the reactive to-do list that Ragnar just demonstrated, the non-shared version of it. You don't need to read any detail in this slide. I will walk you through the important things, and basically there aren't many important things. Basically, we define a bunch of values like remove all, or create to-do, create task, or tasks list, and then we pass task list to a display operation of the UI. What is kind of interesting here is probably that these values can be defined by composing other values, like task list is defined by composing create task and remove all, and these white arrows here depict this used in relationships between values. And at the same time, these arrows kind of depict the paths along which reactions flow. So whenever create task changes or remove all changes, then tasks list will change its value automatically. And whenever task list changes, display will be refreshed automatically. So display will be executed, will be called automatically. What you need to notice here is that basically there are no callbacks, and there is no callback life cycle management happening here in the application code. Everything, this life cycle management or reaction management, happens behind the scenes on the backstage. What you see here is basically the only thing that as a programmer is you see a difference compared to, let's say, Scala, is that we are typing those values with types like event or signal. And basically these are the two main abstractions that REScala offers. Both of them are kind of subtypes of reactives, are subsumed under the type reactives. This double arrowed line here basically indicates that they can be converted to each other. They are composable. I'm saying all of us know what events are, so I'm just explaining a little bit more what signals are. And basically, they are data with time-changing values. Their value changes continuously whenever anything changes on which this data depends, the definition of the computation depends on. Signals can be arbitrarily composed into more complex ones. We call them also derived signals. And REScala also offers a set of combinators like fold and map, filter, zip, and more in order to facilitate composing signals at a higher level. Overall, what you need to keep in mind is that changes along those dependent signals happen automatically and consistently. I'll explain both of them. For now, just take home message from this slide is that the behavior of a REScala application resembles a little bit like spreadsheets. When you change a cell there, any other cell that depends on the value of that cell gets updated automatically. Or you can think of these signals as basically values or functions with a specific evaluation semantic. Most of our functions that we use have call by value semantics. First, the arguments are evaluated, reduced to values, and then we execute the body with those values. We do have call by need in some languages like Scala or Haskell. To give two examples where we have lazy evaluation, arguments are executed only when they are needed during the execution of the function body. And here we have a third kind of evaluation semantics, reactive eval, as I've called it in the slide. Basically, a function is executed, the body of the function is automatically executed anytime one of the arguments happens to change. How does this look like behind the scenes? Basically, the runtime manages the computations and their dependencies in a dependency graph, as shown here on the right-hand side of the slide. There are two kinds of nodes. Basically, the triangles depict input reactives, events, sources of changes, while the circles in the graph, they depict derived signals that kind of are composed out of other signals, be those input events or, let's say, other signals. The nodes in the graph encapsulate user-defined computations, user-defined signals. So the outside world, let's say, never interacts directly with the user-defined computations, but always through the propagation algorithm that manages the graph. So anytime there are input changes, the propagation algorithms starts re-evaluating the nodes in the graph that are affected by this input, that depend on that input, and every time a node is re-evaluated, it invokes the computation defined by the programmer, which may have effects on the surrounding world. So you could think of reactions being managed, just like state is managed in languages like Java or Scala. I also mentioned, so this is done automatically, and I also mentioned that change flows are consistent. What do I mean by this? Basically, it means that a change flow, although it may affect several nodes in the dependency graph, occurs or happens, is executed as if it was instantaneously happening. So as an atomic operation, it moves the entire graph from one consistent state to the next consistent state. And intermediate states are not observable. This can be, it's easily to illustrate here with this flow, starting at the node I, which affects N along two paths in the graph. So the change in I arrives at N along two paths, and nevertheless, the value of N will be written, will be changed only once. So there is this only one semantics because the reevaluations happen in the topological order of nodes in the graph. So all preceding nodes need to evaluate first before N can reevaluate. And yeah, this is this write-one semantics. People also use the term glitch freedom because there is no spurious values, intermediate values that are observable along the execution of a flow. Okay, we have also, so far, we can summarize by saying REScala kind of replaces the programmatic tracking of dependencies between computations in an application with an automatic flow of changes, propagation of changes through dependent computations. And we have also done some preliminary empirical and user studies. Here is the publication of one of them, showing that this has a positive effect on the design of the application, but also on make it easier for developers to comprehend what's happening. What is more, even probably, or the same important is that this shift, this explicit data dependencies managed in the dependency graph, also manifests valuable application level semantics to the language machinery so that the latter can automatically ensure correctness in the presence of disorder. What do I mean by disorder? Disorder occurs, for example, when we have change flows happening concurrently in a multi-threaded environment. Now, each of the flows can itself be consistent, but when they happen together concurrently and have shared nodes in the dependency graph, we can observe glitches again. The behavior becomes non-deterministic, and we want to keep the consistency in this case to have thread-safe flows, which means basically we want to create the illusion of order, the illusion that flows happen, even if they happen concurrently, as if they were happening sequentially. And that's what we ensure in REScala. So we ensure strict serializability without abort. And I will explain in a minute how, a little bit, give you an intuition of how this is ensured behind these scenes. And I will do this by the example of this dependency graph with 3 input nodes and 3 derived signals. Now, the graph stores or maintains not one value per node, but several values of each node. You could say values in different points in time, or one value per concurrently running change flow. So the blue ones that are shown in the slide are the current, let's say at a certain point in time, that's the current value of each node. But then we can have flows that happen concurrently, and before they execute, they kind of establish an execution plan. So they put placeholders in all nodes that are affected by flow, and given the dependency graph, we can determine ahead of time what's the part of the graph that is going to be affected by the flow that needs reevaluation, which means we can establish this execution plan ahead of time. And here the orange starts and puts placeholders in all nodes, kind of signaling or registering, I'm going to reevaluate those nodes, and when I reevaluate, I will fill those empty placeholders with real values. The same thing, assume another flow here, green starts concurrently and starts putting, can do this in parallel, putting its place node holders, and in case those two flows kind of meet at this node N now, we establish the order. At this point, we say, okay, orange goes before green, and this order is established consistently throughout the graph. So if they continue, and let's say it appears that green reaches M before orange, we will swap their order so that they are consistent with the order in N. Now both have established their execution plan and can start now executing concurrently. Let's say the orange flow fills the node I2 and the green flow I3. Now the question is, we reach, I mean, orange reaches N, but it cannot reevaluate N yet, because due to the glitch freedom property, K needs to reevaluate first. The green can also not reevaluate N yet, because it can only reevaluate after orange has been filled. So the only thing that can happen at this point is that K is reevaluated by orange, the version is filled, and now N can, orange can reevaluate N. It does so, and just for the illustration purposes, let's suppose that during the reevaluation of N, the dependencies change. Let's assume we have a conditional in the computation of N, which kind of removes the dependency from I2 and establishes a new dependency dynamically on I1. And just for illustration purposes, assume that now a pink flow starts executing at I1, or starts establishing its execution plan. Now, the propagation algorithm is in control of everything and can do kind of a time travel, establish the execution plan for the pink as if it was established before the orange or green started evaluating. So we put placeholders whenever it is needed. Now all of them can continue execution and eventually reach the state where each node has a new value. Now the fact that this concurrent execution can happen without, we can guarantee there is no aborts, means that there is no observable difference between the behavior of the application running on a single-threaded and running on a multi-threaded environment. That's kind of what I call here semantic transparency. I cannot see any semantic difference. And REACTIVES also ensures syntactic transparency. Remember that I said that all interactions with the outside world are happening through the propagation algorithm, and the transactions, as I call them, they are determined in terms of, or the flows are, the execution of flows is defined in terms of operations on the dependency graph, not on application level state read and write. That means I can change the propagation algorithm with the thread safe one that I just illustrated, and automatically all these APIs that are available to the developers, like creating a new signal, creating a new event, or reading the value of a signal, or setting the value of a signal, all those are automatically kind of executed as if they were transactions. So to summarize, this is a very strong property. Thread safety without aborts, and all this is achieved due to the declarative programming model. And these are, the slide shows basically the features that enable us to do so. The explicit data dependencies enable us to establish this execution plan ahead of time, which is key for avoiding deadlocks and aborts. And the fact that evals run in the topological order extend this deadlock thread safe propagation even to the case where the dependency graph changes on the fly. The write once semantics enable enables pipelining of the execution of the flows. Whenever a value is written, it can be committed right away. And then the fact that we encapsulate the application state into reactive abstractions enables this plug-in thread safety into existing applications, this syntactic transparency. And this property extends to also distributed flows. So if flows run across different devices, they can also, we can ensure that they are run with serializable semantics without abort. Of course, in case of a distributed environment, we need to do more. We need some distributed consensus. The good news is that we reduce the need only to coordinating at the start of a new flow. After they start, they can run without coordination. So we have reduced the amount of coordination and hidden it so that the developer doesn't have to do anything in order to coordinate concurrent distributed flows. Nevertheless, no matter how minimal the coordination needed is, it kind of goes against availability or this, offline availability that Ragnar mentioned. So for this purpose, we also support partition or fault-tolerant flows. And the faults I am talking about are the network partitions and also crash devices, any number of them. For this, we make use of conflict-free replicated data types, CRDTs. They are probably known to many of you. These are specific data, data types or implementations of data types such that the state domain of the data type constitutes a joint semi-lattice. Basically, if I have diverging states, I can merge those without any synchronization because the merge operator, there exists a merge operator with certain mathematical properties. It's associative, commutative, idempotent, so that the merge can happen automatically. Joe Hellerstein added the attribute distributed just to get the acronym ACID, and he calls it ACID 2.0. Anyway, also these data types we encapsulate into reactive abstractions, into signals, and we call those conflict-free replicated reactives. So here is kind of a snippet of the code for the shared to-do application, the one with multiple instances. And the only difference is basically that we use things like replicated list or last writer wins for implementing signals. What that means is that we end up with distributed reactive graphs or dependency graphs, which are connected by replicated reactives here in the slide, shown as pentagons. They are connected across unreliable network connections, and they behave locally just as any other reactive, so they propagate changes of their input to their output, but they also broadcast their changes to their replicas, and once the broadcasted changes arrive, they propagate those locally to the nodes that depend on them. So you could think of these distributed reactives, replicated reactives, as uniformly propagating changes in time and in space. Now, the combination of the reactive programming features and CRDTs gives us synchronization-free eventual consistency of the entire application state without having to model the application state as a monolithic CRDT. So in a typical REScala application, there are several CRDTs, and in order for state changes of related CRDTs to retain causality, they need to happen as if This was an atomic operation. To achieve this, one would have to typically nest CRDTs and has loose modularity. We don't need this in REScala because it's the transactional flows, the consistent flows, the local flows that ensure that the state that related CRDTs are changed as automatically. That means the whole state of the application moves from one consistent state to a bigger consistent state as if it was modeled as a single CRDT. To summarize, basically, the state of a REScala application is typically distributed across different nodes. They can be data center nodes, but they can be also devices. The nodes can be connected via stable connections, depicted here on the right, or unreliable connections. On the side with unreliable connections, the state might diverge. It can get eventually consistent again. We tolerate crashes, as I mentioned, which means that once in a while, a snapshot of the state is taken, and the reactive programming features help us to reduce the amount of state that we need to snapshot. And restorage is basically change propagation again. At the end, the developer can use serializable flows, let's say everywhere on the part of the applications where connections are reliable. It can use fault tolerance flows where there are unreliable connections, but it has to manage this by himself or herself by changing the propagation algorithm or selecting one of the propagation algorithms. And now we are looking at automating this based on some safety properties, safety invariants of the application to derive where actually serializable flows are needed. With this, let me summarize. I introduced you to the few key abstractions of REScala, explained how the propagation happens behind the scenes, how this propagation happens in a consistent manner, in a thread-safe and fault-tolerant manner, and that you can combine those two things within the same application. For more information, you can consult the REScala webpage, where you find more let's say, documentation and a manual and showcases, and also a link to the REScala GitHub repository. At this point, I'd like to thank the rest of the team. You see Ragnar and myself here, but there are more people that have been working on REScala in the recent years. But above all, I would like to thank you for being here and for paying attention so far. With this, Ragnar and myself would be happy to take questions.
So we already had one question by Arthur, who asked if the execution plan has to be established sequentially. And I kind of already posted a small answer, but I want to elaborate a little bit. So the key takeaway, I think, is that Mira has shown you this graph of connected nodes. And because we know a lot about the structure of this graph, the way the execution plan is established is by traversing the graph. And we only need to sequentialize when there's a conflict at a certain node, which will always be on a single device. So sequentializing there isn't very costly because it can just be done like with a lock in memory, which is fine. For the distributed version, this needs a little bit of additional knowledge, namely the kind of the total order of conflicting transactions, which is done by a very elaborate algorithm about like distributed graph testing, which if you want to know about that, read the paper from the 80s. It's amazing. But it's like we can make use of a lot of optimizations here because we know so much about the structure of the program. And for the link to REScala, I put that. And someone else was faster.
Okay.
Thank you for that. currently don't see any further questions, and I believe we are also at the end of the session.
But feel free to contact us at any point in time, and we'd be very happy if people try Scala and we get feedback on what works well and what doesn't work, and yeah, what can be improved and further developed.
Okay. So thank you again. I don't know what I have to do now to end the session, or if I have to do anything.
We need to just leave, I think. We were told, Ragnar, that we just
Oh, we just leave. We just leave.